This is our part 1 circuit. This is a stepper motor controller. We have 4 IC here, which is 74HC107, which is a JK flip-flop, and a 74HC00, 74HCX6, and 74HC08, which is a NOR gate, a NAND gate, and AND gate. So from the stepping sequence here, we can get our output for our stat table. So we fill in the stat table and we have this stat diagram. Whenever the enable input, enable stepping is off, the present state will loop on itself. When the enable stepping is on, the loop will go anti-clockwise from S0 to S3, S2, S1, and back to S0. And when the both enable stepping is on and clockwise is on, the state will loop clockwise, which is S0, S1, S2, S3, and back to S0. So from the stat table, we fill in our K-maps and get the equation for JB, KB, JA, and KA, which is used to connect the circuit that for our part 1. And the output function is obtained by filling the K-map also, which is entering the output into the K-map. So next I will present our result. So the clock is set to 1 Hz, and when the enable stepping is off, this is A, this is B, and this is output 0, output 1, and output 2, and output 3. This is the auto-generate stepper motor controller, and this is the result. When the enable is on, the output goes anti-clockwise. When the CW is on, the output goes clockwise. So next I will generate the clock input manually. So when the output is 0, 1 and the others is off and PA is off, the EN and CW is off. So when the switch is on, the state will loop onto itself. It will not cause any change, and when the CW is on, the output is also not changed. So when EN is on, when the switch is pressed, it will change to state 3, which is 1 and 1. So the output is 0, 0, 1. So in state 3, if the enable and clockwise is off, the state won't change. When the clockwise is on, the state also won't change. If the enable stepping is on, the state will change to state 2. So at state 2, when the both EN and clockwise is off, the state remain the same, and clockwise is on, the state also won't change, and when the enable stepping is on, the state will change to state 1. So this means when the clockwise is off, the state will looks anti-clockwise. So now I'm back to state 0. When clockwise and enable stepping is on, both on, state 0 will goes to state 1 and goes to state 2. When at state 2 it will go to state 3 and back to state 1. That's all.
Now I will discuss the part 2 for our lab, and this is the circuit that we need to do. And at the first, when S2, S1, S0 is 0, the loop will always become 0, 0, 0, 0. And so we are using the second socket to solve the problem. We replace a switch with the ground and change it to the active high, so that it will produce first it will generate first number, and after that we off the switch, become active low again, and it was produce and it will generate another loops. For that loop, we can see from the state diagram, when S2, S1, S0 is 0, 0, 0, it will loop itself, and when socket become active high, and it will become 0, 1, 0, and form another loops for the state diagram. To prove the state diagram, we have to do a circuit to prove it, and this is our circuit. We have drawn a schematic diagram to show what is the circuit we're going on. And for the 3 bits, we are using Q0, Q1, Q2. And the Q2 is S0. We have the equation S3 is equal to S1, S0, S0. So we connect Q2 and the Q1 to one socket and connect to another socket, and the another input is connect to the ground, and the output of the socket will connect to the DSA. According to the datasheet, DSB and the MR is connect to the active high, and CP is the clock. And now we are going to look our circuit. This is the output for the S2, S1, and S0. And we are going to use 74HC164 and 1 XOR gate. And this is our clock switch, and this is the one of the switch which is connect to the XOR gate. At the first 0, 0, 0, when we open the clock, it will still become 0, 0, 0 in the loop, and when the ground is opened at the active high, the output will become 1, 0, 0, and we let it become the ground, and we check the loops with our state diagram just now, 0, 1, 0, and change to the 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, and 0, 1, 0. And this is our sequence diagram for the 3-bit LFSR. From the sequence diagram, we can see that the output is also 0, 1, 0 to 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, and back to the 0, 1, 0, which is here. And from the oscilloscope, we can see that our result is being proved, and it's also a type of the studio random. And for the part 2, we need to do the 7-bit LFSR. And now we are show our circuit. To more easily understand our circuit, we have draw a schematic diagram, so we can know the complex circuit is what the complex circuit is doing. This is the 7-bit LFSR circuit schematic diagram. This is the equation. S7 is equal to S0 XOR S3. And for the 7-bit, we count from the Q6 to the Q0, for the S0 to the S6. So S0 is Q6 with the S3, which is Q3 XOR, and the output is connected to the another XOR gate and with the ground, and the output is connected to the DSA. According to the datasheet, DSB and the MR node is connected to the active high, and CP is the clock. And now we are going to look our circuit. This is the switch which is the which we look in the circuit just now at the ground as the ground. We use this to let the circuit start to move so that it will not have a looping at 0 0 0 0 0 0. And this is the loops for the 7 bits. To prove it's a pseudo random, and based on the oscilloscope, which is the output, we have proved that this is a pseudo random bits sequence. And that's all for our part 2.
This is our lab 4 part 3, and this is our stat graph. This is the table of results, and we have 3 truth tables which come from these results, and we find formulas for DA, DB and F, which can use to find these don't cares. This is our schematic design for the part 3 circuit. The W is the input from part 2 circuits, and the F is the output. This is a real circuit of our part 3 circuit. We use 5 ICs, and the first 2 is from the part 2 circuit. The third one is the D flip-flop, and the fourth one is AND gates, and the last one is for NOR gates. And now the result will generate itself when we connect the circuits to the clock module. And now I will manually manipulate the results. This is A, this is B, this is the input W, and this is the output F. When A, B, W is 0, F is 0, as shown in the circuit. And the next state will go to 0, 1, which is this one. 0, 1, and the input is 1, the output is 0. Next state 1, 0, which is this one. And A is 1, B is 0, input is 1, output is 1, and the process repeat.